One of the greatest achievements of the quantum theory is its ability to explain chemical bonding, and that's going to be the subject of this module. Now, to get started with this, we want to consider some particularly simple systems so that we can get a handle on exactly how quantum mechanics talks about bonding, and then we can get to more complicated systems where we learn something interesting about the quantum mechanics of polyatomic molecules, for example. Now, to begin with, we might consider the union of two hydrogen atoms. Okay, so this is really the simplest chemical reaction that one can imagine almost, where these two atoms come together to form a hydrogen molecule, okay, which we, of course, call H2. Now, let me just talk briefly about what we're looking at here quantum mechanically. We have two atoms here, each of which have atomic wave functions, have atomic states that they're in, and atomic energies. Okay, those are the things that we've learned about back in Module 3. When they come together now, it's all one unit. It's all one thing together. So, for example, I may have my two nuclei here, HA and HB. So these are protons, and so they have the mass of a proton. I'll put those things here. And then circling around them, or somewhere in their vicinity, we've got two electrons. So I've got electron 1 up here, and I've got electron 2, say, up here. All right, now they're not likely to be in exactly those positions, but I hope you'll grant me a little bit of artistic license here. Now, when I start talking about a system like this, I've got lots of things to, that I have to worry about. First of all, I've got four masses here. I've got four particles. Okay, and those four particles are interacting with one another. So, for example, there is an interaction between the two protons, and we'll say that they're separated by a distance capital R. There's also interactions between the protons and each of the electrons. So, for example, this interaction is a Coulomb interaction, an attractive interaction, and we'll say these two are separated by the distance little r 2b. So you can see that I'm using capital letters to designate the protons and numbers to designate the electrons. That way we can keep everything straight. Similarly, I have an interaction between this electron and this proton. I have an interaction between this electron and this proton, and I have an interaction between this proton and this electron. Okay, and all of these things then can be labeled consistently with this number for an electron, letter for a proton scheme. Now, all of these interactions would be hard enough, but we also have this interaction, and this is the one we encountered in multi-electron atoms. And so I'll say that this distance is little r sub 1, 2. So I've got, in essence, 6 different interactions here to worry about, and 4 different masses. So when I start to write down the Hamiltonian for this system, I'm going to have to include all of those various pieces. So for example, for the electron part, I'll have negative h bar squared over 2me, and then I'll have Laplacian operators for each of the electrons. Okay, so this is the kinetic energy of the electrons. I'm going to have a similar term for the two protons, but now there's a heavier mass there. And I'll have del A squared plus del B squared. Okay, now that covers the motions of the 4 masses. These are the kinetic energy parts. What about the potential energy part? Well, these are all Coulomb interactions, and in this particular case, this is simple because all of these particles that are involved here have a charge of E, either plus E or minus E. So I can group all of these things together as E squared over 4 pi epsilon 0, and then I've got negative 1 over R 1a, so that's this first interaction here. I have minus 1 over R 1b, so the interaction between electron 1 and proton B, minus 1 over R 2a, minus 1 over R 2b. Okay, so that covers the interactions of the electrons with the two protons, and these are all attractive interactions. That's why they all have a negative sign. But then I'm going to have 2 repulsive interactions. I have a repulsive interaction between the two electrons, so that has a positive sign, and I have a repulsive interaction between the two protons. I've run out of space here a little bit, but I hope you don't mind that I've crowded this in a little bit to get it all on one line. So let me just again specify. This is the kinetic energy of the electrons. This is the kinetic energy of the nuclei. And these are all the various Coulomb interactions between these particles. They are negative if they are attractive. They are positive if they're repulsive. So this is a pretty complicated differential equation. If we put this into a Schrödinger equation, this is a pretty complicated differential equation to solve. So how can we make some sense out of this? Well, I'll say the first thing that we're going to do is we're going to note that the mass of the proton is much heavier than the mass of the electron. So the mass of the proton is about 1836 times the mass of the electron. So this thing is a massive, massive object compared to the electron. What this means in practical sense is that the electron is going to move much, much faster than the proton will. So in fact, we can think of the protons as moving so slowly that the electrons are responding virtually instantaneously to their position. Now, what this means in practice is that we can, in a sense, almost ignore this motion that's due to these protons and simply focus on the rest of this as an electronic Hamiltonian. So in other words, we can kind of take this total Hamiltonian and separate it into an electronic part and a nuclear part. And in doing so, this piece here represents the nuclear part, but the electronic part, we need to bear in mind, does depend upon the distance between the two nuclei. So we see that distance contained here in this last Coulomb term, but you should also be aware that that distance is implicitly part of each of these separations between the electrons and the two protons. So in other words, there's dependence upon that internuclear distance in here. And so all of the electronic Hamiltonian, all of this part, really is a function of that internuclear distance. We're going to treat it as a function of that internuclear distance, sort of as a parameter that adjusts slowly over time. The nuclear part of the Hamiltonian is only going to be a function of these internuclear distances, because the electrons are moving so fast. It's almost like the self-consistent field method of Hartree-Fock. They're responding instantaneously. They produce an effective potential in which these nuclei move. Well, what I'm describing for you here is a famous approximation, if you will, known as the Born-Oppenheimer Approximation. And it basically says that we can separate the motions of the nuclei and the motions of the electrons. And at least in a mathematical sense, the way we might describe this is to say that the total wave function, which is going to be, in essence, a function of all of these coordinates. Now, I'm using vector notation. That's what the little squiggle under these things means. These are vectors. They include x, y, and z parts to describe the positions of each of these particles. This wave function, we're going to say, can be written as the product of an electronic wave function, which depends upon the two the coordinates of the two electrons, and that this is going to be parametrically dependent upon the distance between the two nuclei. And then there will be a nuclear part, and in this case, including only two atoms, it really has a dependence only on the coordinates of the distance between them. We're going to cut out the translational motion and all of that. So the Born-Oppenheimer approximation is basically allowing us to write this kind of equation for the overall Hamiltonian. Now, having made this separation and made some of these assumptions, we can now write down the Hamiltonian for the electronic part as follows. All right, I'm simply going to, and I'm going to use atomic units to do this. So in other words, now we've got h bar and me and the electron charge and 4 pi epsilon. These are all going to be set equal to 1, so we're in atomic units. So that means our overall Hamiltonian is going to look like this. We'll have minus 1/2 times the sum of the two Laplacians for the two electrons. Then we'll have minus 1 over R1A, minus 1 over R2A, minus 1 over R1B, minus 1 over R2B, and plus the repulsive interaction of the two electrons. Now we will continue to carry this repulsive interaction between the two nuclei in this Hamiltonian, but we need to realize that this is constant in the Born-Oppenheimer approximation. We're treating the nuclei as though they're not really moving at all relative to one another. So that distance will be constant. So it's almost like an added constant onto the energy that we'll get from solving this Hamiltonian, this Schrödinger equation. All right, so the results of this are going to be energy levels for the electronic part that are implicitly functions of the distance between the two protons. All right, likewise, the electronic wave function that we've written up here will depend upon the positions of the two electrons, but it depends parametrically on the distance between the two nuclei. Now, what this allows us to do ultimately, if I write this as an electronic Hamiltonian here, is that I can write a nuclear Hamiltonian also, which would be the one we would solve after solving the electronic Hamiltonian, which would include essentially the kinetic energy of the two protons, and then the potential energy part would be this part that we get from the electrons. So it is parametrically dependent on R, but it becomes a function of R, and that represents an effective potential that dictates the motion of the nuclei. All right, so when we put a molecule together, it causes a little bit more complication in how we set things up, but the Born-Oppenheimer approximation actually is a really great tool because it essentially allows us to do practical calculations to determine the quantum states of all kinds of molecules because we can separate out the nuclei. Now, I want to make a final note here, and that is that the system that we're actually going to be studying mostly in this lesson is a system of H2+. In other words, an ion that contains only one electron. So we have two nuclei and one electron. And we'll be concerned about the distance of that electron with each of the nuclei. But the distance between the nuclei we'll treat as fixed within the Born-Oppenheimer approximation. So when we do this, this means that the electronic Hamiltonian is going to lose some of the terms that we've added here. For example, we will not need a second kinetic energy term. We will not need the distance of a second electron to the various nuclei. And we will not have a repulsive term between two electrons. So that allows us to deal with a much simpler Hamiltonian. So this is the Hamiltonian for H2+. That looks like this. It'll be minus 1/2 times the Laplacian for our single electron minus 1 over RA, so I don't even need the electronic label here, minus 1 over RB plus 1 over capital R. So with this simpler Hamiltonian, we'll be able to solve a Schrödinger equation that will then be used to generalize to much more complex systems.